So welcome to Lecture 7 on quantum field theory. So our today's topic is causality and propagators. So part of our lecture today will be revision or a review of the last lecture, and also we'll be introducing some new ideas and topics. So let's review the idea of causality in Newtonian physics and special theory of relativity. So special theory of relativity introduces the speed of light as the maximum speed at which signal or information or energy can travel. So in contrast, in Newtonian physics, we see that interactions do not have to have an upper limit in which they propagate. As an example, we can take the Newtonian theory of gravitation. In this theory, interactions are instantaneous. On the other hand, if we go to special relativity, we see that the light cone divides space-time into two regions. So in special relativity, we have, suppose, 2 points, say point X and point Y. Now these 2 points in space-time may be causally connected, which means that they need to be inside, Y needs to be inside the light cone of X. So Y could be in the future of X, in which case it'll be in the future light cone of X, or Y could be in the past light cone of X, in which Y is in the past of X. So if Y is in the future of X, then we say that signals can propagate from X to Y, and the point Y is causally connected to X because what you do at X is going to influence Y. Now note that Y doesn't have to be just inside the light cone. It can even be on the light cone. If it is on the light cone, if Y is over here, then signals which propagate at the speed of light will be able to reach Y. Whereas if Y is inside the future light cone, then signals which can travel less than the speed of light will be able to reach Y. On the other hand, if Y is in the past light cone of X, then Y can influence what is happening at X. So in that sense, Y is also causally connected to X, but Y is in the past of X. But we see that the future light cone, the points in the future light cone, and the points in the past light cone, they are distinct. Though they're all causally connected to X, they're distinct. On the other hand, there are points outside the light cone. So for example, if Y is over here, then the distance between X and Y, therefore relativistic distance, is known to be space-like. That means that for this thing, X minus Y whole squared, well, this is squared with respect to the metric, the Minkowski metric. This is less than 0 or negative. Whereas inside the light cone, X minus Y squared is positive, and whereas on the light cone, this is null. This is X minus Y squared is 0. So this is, roughly speaking, the causal structure of Minkowski space. Now, if I make a Lorentz transformation, if I look at a Lorentz transformation, so suppose that I have 2 points, say X and Y, and I'm looking at their interval, which is X squared minus Y squared. So the interval will have, say, for 2 given points, X and Y, this interval is a constant under Lorentz transformation. So let's call that constant, say, a squared. Although a squared can be negative, the square, do not let the square confuse you. So x minus y squared can be x0 is y0 squared minus x minus y three-dimensional dot product squared. Now, if I make a Lorentz transformation, see that, this constant doesn't change. However, x naught and y naught, x and y will go to some other values. So, x naught may go to x naught prime and y naught may go to y prime naught. And x may go to three-dimensional x may go to x prime and y may go to y prime squared, but the difference is still equal to a squared. So if I look at this equation, which is if I, let me just choose, x naught to be 0 and x, the three-dimensional x also to be 0, it's a choice of coordinate system, then what we see is that we see an equation which is t squared minus x squared is equal to a squared. So this is an equation for a hyperboloid. So what this means that if I make a Lorentz transformation, then what happens is that the coordinates or the points on a hyperboloid, so like this, suppose it's in the future and we have some hyperboloid. So this is hyperboloid. So this goes all the way to infinity. So if I make a Lorentz transformation, what will happen is that all the points on the surface of this hyperboloid will move to one another. So for example, if I start with this point, let me use a different color. Let me use yellow. If I move, and if I do a rotation, then the point will just move to another point on the same value of x naught. But if I make a Lorentz transformation which involves a boost, then it'll move in some other direction. So this is to show that all the points on the red hyperboloid are connected by Lorentz transformation. Similarly, all the points on this hyperboloid on the past of the past light cone of x are also connected by Lorentz transformation. And if I take the active point of view in transforming my space-time, then all these points will move into each other. Now, if I look at the points which are space-like separated, such as this point, then we can find that if I do a Lorentz transformation, then all the points on this hyperboloid will also be connected. So this is a hyperboloid. And every point on this hyperboloid can be taken to any other point on the hyperboloid by making a Lorentz transformation. So if I have a point on this hyperboloid, say y, and of course, its separation from x is space-like, we can always find a Lorentz transformation such that x and y, in some reference frame, y will move to a point such that this point y and x will be simultaneous, that they will have the same time coordinate. So, so we see that when we have 2 points which are space-like separated, you can always find a reference frame in which they're simultaneous. So let's just write that down. So if 2 points, space-time points, x and y, are space-like separated, then they're space-like separated, and we can find an inertial reference frame such that x0 is equal to y0. That is the point x and y are simultaneous. On the other hand, if x and y are time-like, that is x and y squared is greater than 0, then we can always find a reference frame in which they are in the same world line, meaning that their x, the three-dimensional x and their three-dimensional y is the same, so that in some reference frame, these 2 points look like if this is x, then y is. As x goes to the future, it goes through y. This is what we mean by x and y being on the same world line. The trajectory, the 4-dimensional trajectory, that is traced out by any massive or massless particle is called the world line of that particle.